Hello, I'd like to welcome everyone to the Sharcnet series of webinars. My name is Ed Armstrong, and our topic today will be Java Threads and Introduction. Now, my goal today is to provide everybody with a basic literacy on the subject of threaded programming and Java in particular. All you need to know to do the Java threads I'm going to be showing you today is just a basic knowledge of Java programming. So what I'll be covering is I'll cover briefly what threads are, then I'll cover how to create and control a thread, some synchronization signals, and then I'll show you where you can find an example I provided for you. What is a thread? A thread is basically a lightweight process that runs concurrently with other threads. Now, lightweight, as opposed to what's a heavyweight process, which is a program running. Now, all threads, they share a node, so they'll share CPUs or connections to a CPU, and most important, they share main memory. They'll share the heap, but not a stack with other threads. You're already using threads every time you use Java. The Java main method is a thread. Java garbage collection is a thread. Anytime you use UI, graphics, or some sort of client-server architecture, chances are you're using threads. Now, up till the advent of multi-core computers, threads were good for convenience programming. They were good for wrapping the blocking client servers and UI to prevent hanging. So it's been around for a while. However, now that we've got multi-core CPUs, we're starting to use threads more and more for parallel programming, which is what we're going to be covering here today. So to first understand how threads work, we'll look at the classical CPU, which is a single-core CPU running 4 threads. So here, threads A, B, C, and D are running over time. They're either running, which means they're executing code, or they're blocked, which means that they're waiting to execute code. So on a single-core CPU running 4 threads, thread A will run until it's done, then thread B will run, thread C, and then thread D. Now they don't interfere with each other, and they're all running at different times. And this is a much more classical. This has been going on for decades. But now that we have parallel programming, or parallel threads and multi-core CPUs, these threads will start running concurrently, which means that thread A might be running at the same time as thread C or thread D, and thread D might be blocking, and then all 4 might run. At times, maybe none will run because they're all waiting for I/O. But the important thing to take away from this is that the number of threads you're running is not necessarily the same as the number of cores you have in the CPU. You can have 4 threads running on 1 core. You can have 4 threads running on 8 cores and not utilizing your CPU. The connection is more up to the programming than it is up to the architecture. So the first thing we're going to cover here today is how to create and control your Java threads. So we're going to introduce the thread class and the runnable interface. I'll show you the first 3 methods, which is thread start, thread join, and thread sleep. And then I'll also be covering the keyword volatile. So there are 2 ways to create a Java thread. The first way is to extend the thread class, and the second way is to implement the runnable interface and pass that to a thread class. Since the thread class already implements the runnable interface, we'll begin there. So the first method, extending the thread class. Here, you can see that example 1, which is our class, extends thread, and this provides it'll be an empty method called run. We then instantiate the thread simply by calling the constructor. No other method needs to be called in order to construct the thread. There's no setup. However, this does not start running the code. To start the code, we call thread.start. What this does is it, in turn, constructs a new thread and runs whatever code is in the run method. This is the same as running the main. So here, in this example, there's 2 threads running. Main is a thread, and then when you call thread.start, run is another thread. And those are 2 start points for 2 different threads. Now, in the second example, we are going to implement the runnable interface. So here, example 1 implements runnable instead of extending thread. So we create a new example 1, runnable interface. We still have to create a thread, but we pass it the runnable, which is example. and then we do thread.start. These are almost the exact same thing, except that there's some subtle differences, which is something you'll get into later on. It's just mostly I want you to know that there are two different ways of doing this. And in examples, you're going to see it flip-flop around. So before we continue, there's three methods that are important to know for the examples I'm going to be showing you. The first one is start, and we've already covered this one, but it causes a thread to begin execution by the JVM will call the run method of the interface. Join will cause a thread to block while waiting for another thread to terminate. Sleep will cause the current thread to temporarily block, allowing other threads to execute. So this first example, we're going to start just one thread. Example 1 extends thread, as we saw before. Now here, we don't save the reference to the thread. It doesn't stop. The thread will run and the reference will exist, but when the run has run out, we'll no longer have a reference to it. There's a subtle difference between keeping the thread as an object and allowing the thread to run. So in the run method, we're going to see two new methods here. It's getID and getName. And what these allow us to do is it allows us to identify a thread. So from the output, it prints out, I am an independent thread, the thread ID is 9, and the thread name is thread 0. I want to point out now that while the thread ID is unique for every thread, there is no particular system that they're assigned. So you cannot rely that thread 8 is before thread 9 or so on and so forth. However, if you want to be able to identify a specific thread, you can set the name of the thread, which we'll be seeing in the next example. So here in this example, we again extend the thread class, and we've also provided here on the second one, if you pass in a string, what you're doing is you're setting the name of the thread. So in our main, we start one without setting the name, and we start a second one while setting the name. And we'll see what we get is two different thread ID numbers and two different thread names. Now it's important to also note that because these threads are running concurrently, there's no way of knowing that thread ID is associated to Albert Threadington or it's associated to thread 0, because the IO is printing out to the IO is what's known as a race condition. And since most of what this talk today is going to be dealing with is race conditions, I'm going to define that now. So what occurs, and this is one of your most common errors when parallel programming with threads. And so a race condition is going to occur when some event, in this case printing to the output, is dependent on a sequence or timings of other uncontrollable events, such as when the thread was scheduled. And this will affect the order in which the threads access I/O, because threads can only one thread typically can access the input-output at a time. So a race condition, and it can occur on a lot of different instances, anytime something matters on the order of execution and it's occurring across two different threads, you could have a race condition. However, just having a race condition doesn't imply a bug. Typically, a bug will occur when you're both reading and writing to a shared variable, and then we want to avoid the race condition, which is what we're going to be dealing with. So the first thing we want to introduce is join. Now, join will block one thread while awaiting for a second thread to terminate. What we're not going to deal with today, but I'll show you here, is that join can also wait for a certain number of milliseconds or a certain amount of time before it gives up on waiting for the other thread to terminate. Now notice that even though there is a join with milliseconds and a join with nanoseconds, the JVMs typically are not precise enough to take advantage of that. I think the typical is about 50 milliseconds that you can get down to granularity. But you know that they're here. So how does join work? That's the question. So here we got two threads. Thread A, main, starts. It runs until we get to start. So it calls start on thread B. And thread B is running happily along at the same time that thread A is. Well, thread A gets to a point where it wants thread B to terminate. So it calls thread B.join, at which point you'll see here that thread A is blocking while thread B is still running. When thread B is done running, thread A will continue. So what it does is it causes one thread to block while it waits for another thread to terminate. And here's going to be a code example of using join. Here, we again extend thread. And it's the same example as the second example I gave you earlier, where we're just printing an ID and a name. However, you'll recall from before that we didn't know which thread was which for the ID and the name. We couldn't associate the two. So we have added, right here, highlighted in red, t1.join. Now its main is the thread calling the join on thread 1. It's an important distinction. So main will wait until thread 1 is done before starting thread 2, giving us the resulting output that you'll get the ID and then the name of one thread before the ID and the name of the second thread, because main is waiting before starting the second thread. Now, stop a thread. And thread will naturally terminate when the run method exits. However, there is no way of stopping a thread otherwise. You have to program this in. Any methods that you see of stop online are actually deprecated methods that have a race condition in them. So nobody uses them anymore. So what we do is we typically put a loop in, or most threads typically run on a loop, so we typically put a flag in that we can switch to make the thread stop. So here, let's take a look at the code. So we have main does stuff to start the thread. What it will do is you'll see the while is running. And then we've added another method called void flag stop. It just flags the stop flag. So what will happen is running is set to false when you do the flag stop. Whatever is running inside the loop will continue. We'll go back up to is running again and see if we want to continue. Now, what's important to note here is this. Up here is the volatile flag. So what's going on with volatile is, what happens is, with the JVM, in order to make things run faster and smoother, it's allowed to put variables into a register. However, if two threads have the same variable in their registers, they may be looking at it and assuming it's a different value. Now, we can solve this with a synchronization block, which I'll be showing you later on. However, it's sometimes more elegant just to make a variable volatile. What volatile does is ensures that the variable is stored in main memory as opposed to being stored in a register. So now, flag stop, the is running, which is accessed by two or more threads, is now a main memory variable. So that loading, now another thing to notice, or to note, is that in Java, loading and storing of variables are atomic. So you'll never, the JVM guarantees that you'll never find a variable in an intermediate state when you load or write to it, unlike C. So here, because it's known to be atomic and it's in main memory, we can guarantee that that volatile variable has the value we want it to. Now, what's important to note there is that this only really works if you're only testing it basically in one line. So we're only testing is false. We're not doing multiple things in this method with is running. In that case, we'll be using synchronization locks. Now, synchronization locks, often called mutexes or mutual exclusion locks, protects a section of code, allowing access to that code by only one thread at a time. We'll be referring to this section of code as a critical section. So here, thread A starts and thread B, they're both running happily along together, but thread A wants access to a critical code section. So it applies a lock. However, eventually, thread B is going to want this lock, but thread A has it. Thread A is currently running the critical code section. Thread B will now block, meaning it's not running, until such time as thread A relinquishes the lock. So now, thread B will continue running and allow it to run the critical code section. Thread A will go about its business that's not in the critical code section. Now, there's 4 ways of applying a critical code section or defining a critical code section in Java. according to the language specification. There are other ways you can do adding other classes, but we're just going to focus on what's known as a synchronized block. Now we can synchronize to an object's method. We can synchronize to a class's static method. We can also apply a lock to an object. Now, because you can retrieve the class object, you can also apply a lock to an instant level, like an instance of a class, or to the actual class itself. I'll just show a quick example of these four methods. So for an instance method, we have a public class example. And in there, and it doesn't have to extend the thread, any method, any class has this built in, is that I can now synchronize a method. That means that only one thread is allowed in this method at a time. If you want it so that only one thread can be in any instance of this method, you can do it through a static method. That means that for this class, any thread can only be in this method at a time, not just for the class instance, but for any instance of this class. Now, a popular way of using synchronization blocks is to synchronize on an object. This is probably the most popular way of doing it. So here, on the top example, we will be passing in an object and we'll be using a synchronization block on that object. So any synchronization block, it can be in multiple methods if you like, that are synchronized on that object means that only one thread can be synchronized on that object at a time. A typical way of doing that is calling the this. Remember that this is the object of the current instance, and you can synchronize code blocks within multiple methods of that instance. So anything outside, not synchronized, not critical. Anything inside, a critical block that only one thread can enter. If you want it so that in the same way that we had static methods, and you want any instance of this class so that one thread can only enter this critical code section for any instance of this class, we will go some class. It actually should be example.class. So you call whatever class you want. .class will give you the class object, and you can synchronize on that like you can any other object. Now, what you really want to use these things for is what's called a wait notify. So we've seen that you can lock any Java object, so that every object also provides an inter-thread signal in the form of a wait notify pairs. The idea works as follows. Thread A is waiting for a certain condition to occur. Thread B will cause that condition to occur and will notify thread A. Now, by design, these wait notify blocks have to be in a synchronization block. Let's just review that one more time. So here, A locks a synchronization block, or enters a synchronization block, calls wait, which means that thread A is now blocking, waiting for thread B to set a condition. Thread B will now set that condition and will enter the lock. Now note that they can both enter the lock at the same time, because when thread A calls wait, it relinquishes the lock. Thread B sets the condition, calls notify. Now thread A is still blocking because notify does not release the lock like wait does. Thread B has to explicitly release the lock, at which point thread A will continue on, and it will also have to explicitly release the lock. Now this might become a bit more clear with a code example. So here is what was going on there. So class A, or thread A, we'll call synchronize. Now I've called it on wait notify.class. It's just so long as they both are calling the same lock, and it has to be the same class that calls the wait and the notify. So the lock, the wait, and the notify are all on the same object. So thread A will print something out while in a synchronization block, and it will be waiting for someone to notify on that object. Class B will lock after the wait has been called. It will set the condition, it will call notify, and then it will exit the synchronization block, at which point A will wake up, continue with what it wants to do, and exit. Now note that we throw or we catch an interrupted exception here. And that's because while waiting, the thread can be interrupted and woken up, at which point the interrupted exception will be thrown. Now, when I originally made this, I actually put a bug into it, completely by accident, but I decided to keep it because it's actually a very common bug that everyone's going to do till the end of time. And that is this thread, if thread B happens to lock first, it will hang, because thread B will look at some condition to be true. It'll set the notify and exit. Thread A will then come along, it will lock, it will call the wait, waiting for a notify that's never coming because it has already occurred, and then continue. What we didn't do here on thread A is we didn't check the condition. We assumed that when the notify happens, the condition is going to be true. But you can't assume that. So to fix this problem, a very simple fix, so we're going to check for the condition. We're going to check wait notify not some condition is equal to false. And while it's equal to false, we'll wait so that when we wake up, it'll see if it's true. If it's not true, we'll wait again. So every time you get notified. However, if we enter this block and it's already true, we'll never call wait. And this will prevent us from hanging. So if you get an unknown hanging while using a wait notify pair, first thing you want to look for is that you actually check for the condition. You cannot rely on the notify occurring and the condition being true. Now, I provided an example online, which we'll walk through a little bit. But it's going to be an example of a master-slave architecture. Now, my caveat is it's not necessarily the best master-slave example. I've tried to make it so that we're using everything that I introduced to you today. But what a master-slave is, it's a very common way of dividing up work. If you've got something that's computationally intensive and you want to apply the same work to the same data, breaking it up as a master-slave is a good way of doing it. The master thread takes a unit of work, passes it to the slave thread, who then executes the unit of work and waits for more work to be given to it. Typically, you have a number of slave threads equal to the number of cores in your CPU. Now, before I switch screens, this example is available there if you want to look at it later on in a public subdirectory. So let's just take a look at it. So here, we'll start with the worker. The worker is a thread, and it will be started by the farmer. It will run. While running, it will wait for work. So while running, it calls iterate. I like to separate the actual work away from the run method, wrapping that method and catching an interrupted exception. It just makes for clear coding, and then you can go down and just do on every iteration you do this. So it synchronizes on the worker while its work, its unit of work is available, does the work, sets it to null, and returns yourself to the farm. Otherwise, you wait. Now, the reason we're synchronizing on ourselves is that we want to be able to tell the worker to stop working. And that, because we have the is running, and the is running is also in run, we synchronize on this. It is important to note that you cannot synchronize outside of the loop, or else you'll never be able to stop the worker. Because if you put the synchronization up here, the loop will be running inside the synchronization block, and you can never enter the stop working method. So when you synchronize inside loops as opposed to outside loops, especially when you're testing conditions to stop the thread. The other place we're going to be synchronizing is when the farmer gives a work to the worker. We want to synchronize on this because the this.unit, remember that this private method is being run by the worker thread. This give work is public, so it could be any thread could be giving this worker work. So we want to synchronize on that so that we are both not testing and giving work at the same time. The unit of work here is basically just so that it had something called a unit of work. It's a runnable method. It could be anything you want. You extend it as appropriate. So the farmer itself keeps track of, and you're going to see why we synchronize. It keeps track of the workers and the work waiting, and it's the farmer's job just to give out work. So when you add work, now the farmer itself implements runnable, but it's not necessarily a thread. You don't have to put the farmer in a thread. He simply coordinates threads. So when you run, we'll do for every worker, he starts all the workers. While there is work waiting, so while work waiting is not empty, I again call the iteration so that I can wrap this interrupted exception, and I'll give out work down here. Now note that I'm synchronizing on idle workers. Idle workers is just an object up here. Every object can be synchronized on. And the reason I'm doing that is there's a callback function that the worker will call add idle worker, passing itself and adding itself to the queue. So because that this add idle worker thread, or this add idle worker method, could be called by other threads, we have to wrap anything we're doing there inside a lock. So here, they're both wrapping the idle worker lock. It works while not is empty. It's waiting, so it says, oh, I need what? There's no idle worker, so we've got to wait notify here. What this does, so the idle worker here says there's no idle workers to use. I'm going to wait. When a worker adds itself to the idle worker list, it will notify. So it will notify and then exit this lock, at which point we will continue. Now, notice that there is a while idle workers is empty. So while it has been notified, we are still going to recheck our condition before we continue to prevent hanging. Then we go down, we remove the idle workers, we're still locked. We've now locked the idle workers queue, give it some work, and exit. So, note that we've got 2 synchronization locks and 2 wait notifies, and never the twain shall meet. If they do meet, and this is going to be the subject of a future seminar, is that you're going to possibly get a deadlock condition. And that is when because I'm using 2 locks here, and if you use 2 locks incorrectly, you could prevent anything from happening. But we'll just take a look. If you want to see the farm, it runs by starting up farmers. I've started up 10 threads. That is, again, independent of the number of CPU cores we have. And then I give them random work. And then we just start farmer.run. Now note that farmer.run is not in a thread. So it's one of the advantages of using the runnable interface over extending the thread class, is that now the farmer running is just part of the main thread. If I did instead new thread.start farmer, we would now be putting the farmer in its own thread. It runs the same, but now the main thread and the farmer thread are separate. I invite you to go back and take a look at this again. Go here and take a look at this code. Feel free to use it. It's not necessarily the most efficient code, but it's a good example. So I would like to thank you for listening to my seminar, and I invite any questions.